Yeah, okay. I will do this presentation in English, so everyone in the consortium can actually listen to it. So I hope that's fine with everyone. I will present you Squirrel, which is our internal data loading tool today. And yeah, that's why I call this talk Squirrel meets SafeTrain. And yeah, happy to have you today and to bring you this tool a little closer. Let's start this talk with an agenda. So I'll briefly motivate the talk and what we're dealing with here. And then I'll introduce what is Squirrel and why we use Squirrel in our day-to-day business and in our research department. And I also how you can use Squirrel in your workflow. And I'll end with a concluding remark. Just one question. Do I have 30 minutes or 45 or like the whole session?
You have typically the whole session.
Okay.
There's no thing that there are multiple of talks, so.
Cool. Thank you so much. Then I don't have to look at the time so much. Perfect. So let's start with the motivation of this talk. As we know, machine learning is all about data and feeding the beast. So I have this slide from our engineering lead, Thomas Wollmann, who gave a talk on Squirrel at PyData at this conference that happened in the summer. And essentially, this shows the typical machine learning pipeline in an abstracted way. So first we go from raw data, which is like our raw cookie dough, to our training data, which is the processed cookies that can then be ingested by our model, which is the beast. And the beast usually sits on GPU, which is very fast at processing the cookies. However, there's one typical problem in machine learning and training these machine learning models, which is GPU stall. Here in this graph, you can see on the x-axis the time and on the y-axis the GPU utilization. And you clearly see that the GPU is not fully utilized. You see individual spikes that probably correspond to the individual batches that you're processing, but there's a lot of downtime in between, such that your GPU is actually not used to the full extent. And there's a problem, of course, with that, that your training will take much longer than if your GPU was fully utilized. And that, of course, also means a higher training cost for a model, because usually you don't pay on like a research cluster or so, you don't pay per sample processed or so, but per GPU hour used. And if you rent a GPU for many, many hours and utilize it very low, then that can be a problem in terms of cost as well. So we really built this data loading tool in order to improve the GPU utilization and also other things as well, which I will touch upon later. But on the right here in the graph, you can see like a good GPU utilization, like usually you want it between 80 and 100% or so. And there will be like the usual down spikes here for example, when you switch data loaders, when you switch from training to validation or something like that. But yeah, this would be a much higher GPU utilization that you actually want. And yeah, this is a really interesting metric to look at. Weights and biases, which is a very advanced logging platform, comes with a whole lot of system metrics, and I can really recommend you to look at that before or after training your next model. It really makes a great difference how you utilize your GPU. Let's look at this at a bit deeper level. So how does this training pipeline look under the hood? So I have this graphic from a paper that's linked below. Essentially, there are three rates that we really care about in data processing. and data ingestion, which is the fetch rate, essentially the samples per second you can load from the disk. There's the prep rate, which is the number of samples per second you can pre-process. So probably you want to transform your data from, let's say, a NumPy array to a torch tensor, which then is probably like maybe randomly cropped or randomly rotated or something like that in a data augmentation, and then collate it into a batch so that your cookie is ready for ingestion. And then the last piece of the puzzle is the GPU. There's someone who's not muted. Could you please mute? That'd be great. So there's the last piece of the puzzle, which is the GPU rate on the right side of the graph. And usually that would be probably your fastest part of the pipeline. And as we know, there's this German saying that a chain is only as stable as its weakest part. And the saying also holds here, like this pipeline will only be as fast as its slowest component, essentially, because the other components will be bottlenecked by it. And there's this interesting fact from this paper down here that says DNN spent up to 65% of the epoch time in data preprocessing, primarily on redundant decoding, and then, well, the GPU sits idle for most of the time, which causes problems or costs. Let's look at this pipeline and its implementation on like a bit more deeper level. This is a naive implementation, how people might want to implement their data loading pipelines. First, you would fetch your data from the disk, you would decode it into some useful format, and then transform it into whatever format you want your GPU to be fed with. Then you shift that data to the GPU, and you compute your forward and backward pass on the GPU. And that's for one batch. And now the second batch will be processed analogously, but sequentially. So you can see, or you can imagine, I don't know if you see my cursor, but you can imagine like this GPU spike at this forward and backward pass where the model is actually processing data, or the GPU is actually processing data, and for the rest of the time it sits idle. But there's the better implementation of this, which machine learning practitioners usually go for, which is the multiprocessing setup. And you would here, for example, have 4 worker processes, worker 0, 1, 2, 3, that all in parallel compute this fetching, decoding, and transformation of your data. And that would usually yield you a higher CPU utilization, so you need, of course, more compute power in order to do this all in parallel. But the benefit of all this now is that you would have a queue that can be filled with the data on the fly that comes out of these worker processes. And then all the GPU needs to do in the main process is like take these batches that are ready for ingestion and fetch them onto the GPU and just compute its forward and backward passes. And now you can see we like greatly reduced essentially the time or the time difference between these red blocks from the slide before here to the slide after, where we get essentially more things happening on the GPU. But there's also a problem here, and this will motivate this talk as well. So what the problem here might be that these worker processes are not fast enough to fill up the queue and keep the GPU busy. So this is a typical scenario that the GPU is still faster than your data loading in the worker processes. So you will still have some idle waiting time until this queue gets filled up with the next batch. So enter Squirrel. Squirrel really aims at, so one goal of Squirrel is to reduce the fetching and decoding time in the worker processes. So if you go from the first slide to the second slide, you can see that we are reducing the time here that it takes for the data to be fetched and decoded. And that also means we get a queue that is filled up more quickly. And that in turn, of course, means that we have a more busy GPU if we assume all things being equal, all other things being equal. So now let's have a look at what Squirrel actually is, how it does all this, and why it might be interesting to you. Squirrel is a open source Python package that we developed at Merantix Momentum. It was initially started via internal projects that were requiring to process very large amounts of data. And then we really took this tool from this one project and scaled it to other projects, and then decided to share it with the open source community because it really makes a difference in deep learning pipelines. And I think that could really make a big impact in the world. Even if you think about how many people are using GPUs and how many people are not using the GPUs to their fullest extent around the world, that could make a big difference. So there are 4 USPs, I would call them, to Squirrel. First is the speed. So we are really designing this tool to avoid GPU stall. Cost, as I said, the reduced GPU time will cost you less. And also, there's another cost-cutting factor, which is the loading of the data in bundles. So usually you would fetch your sample, your dataset sample by sample from the disk or from a remote storage. And if you imagine you have a dataset of 100,000 samples, you would have to have 100,000 I/O calls to your remote storage if your data is stored remotely. And that will also incur a lot of cost because platforms like AWS or Google Cloud, they will bill you per item accessed. And what Squirrel now does is package these individual samples into useful bundles that can be downloaded as a whole. And that will reduce your cost of training a model also drastically. And there's also great flexibility that comes with Squirrel. So we can customize the data schemes that I will showcase in a second. So you can really tailor it to your data. And it also enables great collaboration and data versioning. So these are the 4 key USPs, I would say. There are 3 key components to Squirrel that build up the pyramid of Squirrel. So at the lowest level, we have the iter stream, which is the API that Squirrel is designed around. And that's a very powerful API that I will present in a second to chain different calls and transforms that you might want to do on your data loading pipeline. The driver is essentially the tool that fetches the data from the disk, and that will be specific to whatever data format you use. And then at the highest level, we have the catalog, which is a dictionary-like data structure that maintains data sources and is shareable. So the catalog will be also showcased in a second, but the collaborative aspect of Squirrel that I was touching upon really comes in to effect at the catalog level. So let's see what these 3 components are. First, we have the IterStream API. There will be a bit of code in this presentation. I hope it's fine for everyone. If there are any questions, I'm happy to take them. So this would be like a typical example of the IterStream API. In this row here, you would have your data source. That could be a driver. Here, it's just an iterable source around a long range of numbers. So numbers between 0 and 1999. And then you could call all sorts of different useful methods on this class. Iterable source, as you can see down here, is a subclass of composable, and composable is basically offering all the API that Squirrel implements. And these different method calls here are all implemented by the composable class. And you can, for example, shuffle your data on the fly. You can filter your data. This is really like, yeah, functional style programming here. Filter your data. You can map any function over it, over this iter stream that you want. So for example, you could do your data augmentation here. And then you can even have an async map, which would spawn a thread pool and then execute any task that you give it here, any function that you give it here on this data stream in a thread pool. You can also specify a process pool here if you need more power. And then you would finally usually want to batch your data into batches of, say, 100. And that defines your iterable. This is like a thing that you can now hand to your machine learning pipeline. And how you would usually iterate over this is with a simple for loop. So this could be your training loop here. And here I'm just checking if the data that comes out is actually of size 100. So this is now a list of size 100 because we batched it into 100 items per batch. And those here on the left are like the basic stream manipulations that you can do with Squirrel. There are several more advanced ones. Async map I've already touched upon. Dask map is a great one. So if you have very, very expensive computations, you can offload them to a whole different cluster with Dask. Dask is essentially like a software that helps you with computing in the cloud. And you can also call loop over it to like have an infinite stream of data. Monitor helps you to monitor the throughput of your pipeline. And there are many more stream manipulation functionalities in the IterStream API that you can read about in our docs or that you can talk to me about. So let's move on to the second part of this Squirrel project, which is the driver. The driver is another key component, which, as I said, fetches your data from the disk, essentially. So you would usually select one of the drivers. Usually you go between the message pack driver or the JSON-L driver. Those are two different formats for encoding data on the disk. And we've implemented these drivers for our users that do the decoding of the fetching and decoding steps, the two steps that you've seen on the previous slides, in a very efficient manner. And there are also other drivers like the file driver, which just loads a single file, or the CSV driver. So if you have very, very large CSV files, you can also use the CSV driver for that and have a Squirrel pipeline over it. And yeah, one thing to note here is that we can do both local loading as well as remote loading. So by local loading, I mean you're fetching the data from the hard drive of the computer or node that you're sitting on. And by remote loading, I mean you're accessing like a bucket, for example, that is hosted on Google Cloud. And then the data will flow through the machine learning algorithm via the internet, essentially. And that will usually take a little bit longer. However, you get much more flexibility out of that, of course. And here on the right, you can see that local loading is faster than remote loading. And also, probably the more interesting fact is that the message pack driver is much, much, much faster than the JSON-L driver. So both for text and images actually. So you probably want to go for the message pack driver if you are dealing with text and images. About other modalities, I can't really say much at the moment, but the great thing is that you can easily implement your own driver if you have your own file format or data formats. Maybe you want to have, encode like, I don't know, let's say Excel files or something like that. Then you can easily write your own Excel driver and then use that in your pipelines. And the fun fact is that the Excel driver is actually already in Squirrel. I don't have it in this slide yet, but we're adding more drivers as we speak. So stay tuned for more work on this. And another great thing I want to share with you with regards to the drivers is that we are integrating several data loading platforms out there and are sort of unifying them underneath the ITOStream API interface, API without interface. And so these the three main platforms that we speak about here are Hugging Face, Active Loop, and PyTorch, Torch Vision. So you might have heard about these platforms. They are really hosting datasets online, especially Hugging Face and Active Loop. They have like a great community-based approach where people who like publish papers and want to share their datasets, they offer a possibility for them to store this data online and make it accessible for anyone. And then, of course, all of these three different platforms come with their own data loaders. However, we've written wrappers around them, so you can easily access any dataset on Hugging Face, any dataset on Active Loop Hub or Deep Lake, and any dataset on Torch Vision with a single line of code. And the great thing here is that you don't really need to get used to the API of the individual framework, but Squirrel does the work here for you. And yeah, that's really great because you have like an enormous amount of datasets, open source datasets out there to choose from. So if you are just implementing a machine learning pipeline and you want to access datasets from there, from these platforms, you can go for that easily. The third, I would be reading water, sorry. The third component of Squirrel is the catalog API. As I said, this is the component where we believe this shareable notion or collaborative notion of Squirrel comes in. So in the Python code on the left, you would define a catalog as follows. So first you have a source, like a data source essentially, that has a name of your driver, for example, the Hugging Face driver that you used, the URL where this data sits, and then so also some metadata like your author, your license, or for example, your version of your dataset you could also store there. And then you register the source in the catalog, and one catalog can store many sources. So that's also nice. If you want to chain multiple datasets together, you can do so easily with Squirrel here. And then what you would usually want to do is write that catalog to your disk. So you would obtain like a YAML file, like shown on the right, that shows you your driver name, your URL, etc. And how and why does this now speed up our research workflow, or how do we use it in our company? Some words on that. So I want to continue with the catalog idea here. So these catalog.yaml files are really an interesting way of sharing data. So each developer or each project will have their own remote file storage in our cloud infrastructure. And we can call this data mesh, for example. This is like a term that we want to coin here in that regard or in that area. And these catalog YAMLs are essentially just references to these individual remote file storages. So as a developer, you would create your dataset on your own remote file storage. And if you were to share this dataset with someone else, you simply create a catalog.yaml file that contains all of the information that anyone else would need to access it. And then you can share that with the Merantix research team, for example, or anyone in SafeTrain, and they will be forwarded to the correct remote file storage upon reading from that catalog with Squirrel again. And that's really great because this is pushing the paradigm of like decentralized data storage. So there's this argument that having every data piece in one place is not so good because this could like lead to a single point of failure, essentially. Like if there's a hacker problem or like a data leak or whatever in your one part of your storage, then that would like affect all of your data, of course. However, if you have this like decentralized approach in the data mesh, then that can be alleviated. And you do need a good way of referencing what sits, essentially. So that is where Squirrel really helps you out. And yeah, now I want to also share some of the benchmarks that we've done on this tool. And this, yeah, is essentially also a reason why we use it in our research team, is because Squirrel is very, very fast. So here we are comparing against like the major other frameworks out there, which are Torch Vision, Web Dataset, Hugging Face, Active Loop Hub, and FFCV. And if we're loading Cypher 100 images, which is like a standard benchmark, probably not the only one out there, but one at least, and you see that here Squirrel performs very, very good, like approximately on par with FFCV, maybe even a bit better one, maybe even a bit better. And in the right graph, you can also see the same phenomenon for text data, where we load the Wikitext 103 training data set. And how does this look for remote loading? So this is also a thing that was very important for us. We don't always like want to copy data sets around. We are really like a cloud-first company, and rather than like fetching huge data sets around all the time, we rather want to have them in one remote location where everyone can access them. And Squirrel allows you to access these remote storages at a very, very high speed. So you can see the comparison against the other frameworks that can do this, which is Web Dataset, Hugging Face, and Active Loop, and they are much, much slower here. And the other frameworks like FFCV and Torch, the PyTorch specific ones, they don't even allow you to load remote data, which is also unfortunate, of course. One more sip of water. So now let's look back at our multi-processing pipeline with Squirrel. And I wanted to share one last feature of Squirrel that is particularly interesting, I think. There's one thing in here that still looks a little bit long, which is this transform part here, the yellow one, which is concerning data augmentations, for example, that you do on your data, the random rotations, random crops, etc. And how can we speed them up? Dali, which is a framework by Nvidia, helps you in speeding up these transforms by computing them on the GPU. You can also do them on the CPU. However, Dali is famous for implementing these data augmentations at a very low level in C++ code on the GPU, and that means you can process your images even faster and prepare them such that your queue is never empty, and your GPU can then directly load the data and process the data in the forward and backward pass in the main process. And we've tried and tested this. So Nvidia and Squirrel, Dali and Squirrel really work together nicely. What are the benchmarks on this? So if you were to process your image, for example, of this like typical computer graphics image into that one, which is like a rotated and it's a like crop and sheared image, then you get the following results on the right. If you compute it with Torch Vision and NumPy, you get like a 2 or 3K samples per second. If you do it with Numba, which is like a compiled version of NumPy, which takes quite a bit of effort to implement, I would say. It took me a while. You get a better performance than Torch Vision. However, if you use Nvidia Dali, that offloads all of these augmentations that are expensive onto the GPU, and then also benefit from like batching onto the GPU directly, then you get a much higher throughput. And also less GPU stall, of course. And what's also very exciting that I wanted to share with you is third-party benchmarks. So these benchmarks that I've shown you now, they were, of course, run internally. And it's also interesting to see what other people do with our tool. So on the left, probably the most exciting one is from ActiveLoop. So the company that builds these two data platforms, Hub and Deep Lake, that we also integrate in Squirrel, by the way. And they show that, Squirrel is a bit slower than their platform. There's a paper out there that is not yet reviewed. It's a preprint that shows some results, but I think, it's great that we come out faster than FFCV and WebDataSet and the other standard packages out there. And I mean, this is one sample, right? So I think it would also be interesting to find out what the exact settings were they ran these experiments with. They have like virtually no information on that in the paper. Like, did they use the message pack driver or the JSON-L driver, which makes a huge difference. So I think, the overall rough result is looking great. So we're at least in the front. And we have to say, like, this is really more of a side project here at Merantix Momentum. We don't have anyone working full-time on it. Like, we do have a core developer team, but everyone is like mainly staffed on other projects, and we like develop Squirrel as we speak and as we think it's useful. However, we don't have anyone like working on it full-time or so. And another cool highlight here I wanted to share is that ActiveLoop has showcased these results you can see on the left on Neurops last week. And so on this like little poster presentation here, this person is holding, you can see that this graph is also depicted. So even though we haven't published a Neurops paper or anything, we still made it to a Neurops poster. But I really hope we will be able to publish an academic paper on this in the near future. And we also have to note that this is a preprint and this is not yet published by ActiveLoop. And on the right side, we have a similar situation going on where someone has done a performance analysis of different data loading tools. And we've read this paper extensively, and we do think there's something wrong there, because basically all of the different frameworks are the same across different batch sizes, and yeah, this kind of suggests that there's another bottleneck in the pipeline, maybe the logging or something like that, that keeps these frameworks at more or less exactly the same level. So, to be honest, I personally, yeah, I'm viewing these results with a bit of caution, but let's see if there's a review of this paper, or maybe even yeah, publishing at some point. However, we've already contacted them and are in discussion about the code that they've written, which is also open source. And yeah, stay tuned for more information. The last 2 slides here in this talk are the ones on how you can use Squirrel. So how do you integrate this into your pipelines? And then I'll finish with conclusion. So let's see how you can adopt Squirrel. On the left side, you would usually have your native PyTorch data loading code. For example, you have an iterable data set that returns some iterator upon calling the iter method. And then you have a for loop, which is your training loop, and you iterate over the data that the PyTorch data loader gives you. And what do you now need to do for Squirrel? So first you need to bring your data format from this left like structure into like a sharded version. So as you can see here, like you usually have like all of the images lying around separately on your disk, and then Squirrel will ingest this type of data and batch it into shards. So in each of these shards that end with a GZ file name, there would be, for example, 100 or 1,000 images and image label pairs. And yeah, so everything is nicely packaged up together. And then you have some URL where this data lies, for example, on your cloud bucket. GS stands for Google Storage. And then you can ask your message pack driver to return the iterator over this, or rather the iterable. And then you need to feed that to your data loader, which will then convert it to an iterator, and then you can use the iterator down here in the training step. And that, yeah, is basically already giving you more speed out of the box. Allows you to load data remotely very easily from like cloud systems like AWS, Google Cloud, Azure, and so on. And then you will also be able to benefit from our expressive API. There's yeah, one conclusion slide that I have for you. And yeah, this kind of like sums up my talk. So Squirrel is this open source data loading tool by Linux Momentum, which offers 4 USPs: speed, reduced cost, flexibility, and collaboration. If you want to install Squirrel, there are 2 main repositories: Squirrel Core, which is basically yeah, the main package that you want to install if you want to use Squirrel. And then Squirrel Datasets implements some like more specialized drivers, for example, these Hugging Face and Hub drivers. Thank you so much for your attention. I just remembered that I have skipped a slide for some reason. I will present this before finishing. So, how do one more benefit that I wanted to share with you of Squirrel is that you can easily share datasets. So, we're writing papers, and with some papers there will be new datasets. And for example, with this new paper that we've presented in a workshop at ICML, there was a new dataset released, and then all we needed to do is on Squirrel datasets in this public repository, share essentially the catalog YAML for this project, and then like the world can use our dataset very easily if they use Squirrel. So this is really also a great aspect in terms of research and reproducibility. And yeah, I hope I didn't bore anyone, and there are still some people in the call. Yes, there are. And yeah, happy to take any questions in the last 15 minutes.